Okay, right, so let's get going. Welcome again to today's course, and we're in the middle of doing some theoretical molecular physics. Last week we've been talking about the Born-Oppenheimer approach, and I explained to you when this approach breaks down or when it is still valid and when we can use it. So if we can assume that our electronic states are sufficiently far apart in terms of energy, when comparing these energies between the energy difference between these potential energy surfaces to other types of excitation, namely vibration and rotation, then we're on the safe side, treat the problem separately and assume an potential created by the electron cloud that gives us energy as a function of the coordinates, and in this set of energy as a function of coordinates, so this potential energy surface, we can solve the Schrödinger equation for the nuclear part and get the vibration. I also mentioned last time that handling the vibrational part is not the big issue. The big issue is to calculate the actual potential surface you need in order to do the vibrational analysis, which means basically the process of solving the electronic Schrödinger equation for several types of geometry, for several geometries, because you want to have a local approximation to your potential energy surface in order to find out about its curvature so that you can do the vibrational analysis, right? So it's not enough to just have one point on the surface. Typically, you want to know your surface in some proximity around the minimum energy geometry. So if you think about the two atomic molecules, or some diatomic, we said the only degree of freedom with respect to nuclear coordinates that matters for the energy is the internuclear distance, right? And if we do a scan, we get the potential curve. And this curve shows a minimum somewhere, which we call then the equilibrium distance. And so at the equilibrium distance, I would like to know also points in the, like nearby, so that you they can apply a fit, for example, and get the harmonic approximation for this vibration, right? So you do this either by scanning over the potential energy surface with some grid, or if you need the full surface information, sometimes you can use, you can take advantage of certain geometries, right? So if something is highly symmetric, then your changes of the geometry in order to get and learn about the whole potential energy surface is a smaller area, right? Because you know how the potential energy surface will behave at this other part due to symmetry, for example, right? So this helps a lot because it reduces the amount of points needed to learn about the potential energy surface. Okay, so let's get now going with the electronic problem. And the tradition to get into this topic is to discuss fundamental problems from a historical perspective. It's H2 plus and then later H2. So the very simple system consisting of two protons and an electron will be our first system to look into. And for this, I'll take this first slide, go to full screen mode, hopefully. Yes. Okay. So you can see the hydrogen molecule here. We have nucleus A and B, internuclear distance RAB with R capitalized. And then we have in lower caps RA and RB, which is the distance of the electron to the proton A or proton B. Now, if you separate this problem and just look at a single electron in the field of a proton, we have a Schrödinger equation that looks like this. The Hamiltonian consists of the kinetic energy operator here for the single electron, and the potential term, which is the Coulomb potential of 1 over R, and the corresponding eigenvalue of the Hamiltonian, the energy of the single hydrogen atom, is denoted as E naught for A and E naught B for the other one. And since it's the same type of atom, it's the same energy E naught. Now, if we leave the nuclear-nuclear repulsion for now out, which is simply a constant to be added, because if we freeze the geometry, right, if we just solve the electronic problem for a given geometry, RAB is fixed, and therefore the Coulomb repulsion that stems from the nuclear interaction is simply a constant that can be added to the total energy. So we have a Hamiltonian that looks like this. In the case of having the electron now placed in the field of both of the nuclei, kinetic energy and the two potential expressions, 1 over Ra, 1 over Rb. And the idea now, and this is a very prominent and very useful idea, is to say that we can probably get a reasonable ansatz for our electronic wave function in this specific case by making a linear combination of the atomic orbitals. So the atomic orbitals are our exact solutions of the Schrödinger equation for the electron in the central field. So we know these solutions. You have discussed this, or you have seen this before in previous lectures. When you did it explicitly, you can show and solve the Schrödinger equation for the electron in the Coulomb field analytically, and you end up with a combination, a product function. Due to the symmetry of the problem, its high symmetry, the angular momentum is a conserved quantity, so you know it's a product of a spherical harmonics with a radial function which is described by the Laguerre polynomials, and together they give you the solutions which we then call the orbitals, right? We have 1s, then we have 2s, 2p, and so on. So these are the solutions, and these will be these orbitals will be our tools or our components from which we construct our electronic wave function for this molecular system. And in this simple first example, we will use these atomic orbitals of hydrogen to build the molecular orbital for this, or the total wave function, if you wish, the total electronic wave function of this molecule H2+, which is a simple single electron wave function still. So we write psi as a linear combination of both eigenfunctions. We call them phi A and phi B. And we can basically write then our Schrödinger equation for this system as on the left-hand side we have the we have the operator acting on this product now of C1 phi A plus C2, the other coefficient, times phi B. And we write it in the way as it's shown here on this slide 96, where we can identify basically, okay, if I look at how the operator acts on the first part of our wave function psi, I see that this operator is actually my atomic operator HA, which I have in case of having a single electron around just a proton A, and the other part just changing the order and identify that this action on my orbital phi B is HB plus, and then comes the other interaction which stems from the proton A, for example, right? So that's what I have on the left side. On the right-hand side, I have the corresponding energy eigenvalue multiplied by my expression for the total wave function, for the total electronic wave function. Okay, now I'll bring the energy expression E to the other side and just subtract it from E naught, which I have introduced because I know already the solution for this operator part HA and HB, because these are this is the Hamiltonian for the atomic system, right? And for this we know the solution. It is E naught because phi A is an eigenfunction of this operator, and phi b is an eigenfunction of the operator HB. So we just denote this difference of energies now as delta E, and you see what remains is now a set of equations. If we multiply from the left and from the right, once with phi A star and once with phi B star. So I'm multiplying this expression, so this atomic orbital phi A from the left, giving me the first equation, and if I multiply B, I'm getting this second equation. So we have these energy differences, delta ES, and we have used shortcuts for the integrals that appear here. There are basically two types of integral. One is a type of integral that gives us some value simply by integrating over the product of the two atomic orbitals. Excuse me. Of the two atomic orbitals, phi A and phi B. We call this the overlap integral S. And S appears whenever our term that we were working with did not depend on any of the electron coordinates, which was the case for the energies or the differences of the energies. So this is where our S appears. And then we have this other type of integral, two different flavors. One would be the Coulomb term for the proton B sandwiched by a orbital phi A left and right. So you see this is what we call a Coulomb type interaction. So it's a term where we have the 1/r term multiplied from left and right with the same type of atomic orbital. And the other thing that can happen is an integral where I have two different orbitals meeting, and the integration over this electron in phi A, but on the right hand side in phi B, right? So we can call this first integral, where we have phi A meeting phi A in the integration, the Coulomb integral, and the other one, the exchange type integral. Okay, so this is a fundamental difference, and it stems from our idea that we have phi A and phi B as parts in our construction of the actual new electronic wave function for this molecular geometry, where we have the two protons and one electron. And if you look at these integrals from a classical point of view, then this Coulomb type integral makes perfect sense, because if you take phi A and you multiply it with itself, so you take the square of the wave function, it becomes something that is proportional to the probability of finding this electron somewhere in space. Since the electron has a charge, it is a charge distribution in space. And what we are doing here is to integrate the charge distribution, which stems from this electron that's orbiting around the molecule and gives us this spatial distribution over space, and the interaction with a point charge, a positive charge, the proton positioned at the position of nucleus B, for example, in this case. And so this is a classical expression. It's simply the energy of a smeared out electron or charge distribution in space given another point charge with positive charge, right? So this is the Coulomb type, and the other one is an exchange type integral, as we call it. It is an integral that stems or that mixes basically two wave functions, namely the one that is the eigenfunction of the atom A and the other one of the atom B. So this is our set of equations. And
can I ask a question?
Sure.
About it? Can they be complex valued?
Yes, they can. And it depends on how you treat this computation. In principle, they can be complex valued, but in the problems that we are typically addressing, we can choose a real representation for our wave functions when we build the total electronic wave functions.
Okay, because if they were complex valued, then the first one wouldn't really correspond to the absolute value.
This is correct.
But
yeah.
yeah. Okay.
Mm-hmm.
Okay, but thanks.
Okay. So now we solve this set of equations. It is a set of two equations, and it's a homogeneous linear set of equations. So non-trivial solutions only exist if we take the determinant and set it to 0. So from this follows constraints or conditions for the coefficients in our coupling. And we see that for the case of choosing C1 equal to minus C2, we have a total wave function for our single electron in the field of the two nuclei given as C times phi A minus phi B, and the corresponding energy in this case is the energy of the atom, so the energy of the electron in the field of a single atom, plus, and then comes this term C minus D over 1 minus S. And the other solution for C1 equals C2, so we have a constant C multiplied by the sum of phi A and phi B. So this is obviously a symmetric wave function, meaning that if I change here so if I would plot the wave function, or you can say it this way, if you make a particle exchange, in this case we have only one electron. So if you look at the wave function in space and you look at the value of the wave function as a function of position in space along the internuclear axis, then you see one of them looks like this. This would be then the antisymmetric wave function, and the other one would look like this. That would be the symmetric wave function. So each of these two wave functions has a corresponding energy, and we see it's different from E naught because we have this coupling term. And in both cases, it is dependent on the integrals that we discussed, the Coulomb type, then this exchange type, and then 1 minus S, with S denoting the overlap. Okay, and if we look at them, well, you can see it here. I just showed you before with my finger. So that would be the symmetric wave function that we are forming by having just a summation of phi A and phi B to give us this symmetric wave function. And the antisymmetric one is the difference between the two, leading to this shape. And you can already see that if you take now the absolute square of this wave function in the case of the symmetric wave function, there is a non-vanishing probability of finding electrons between the two nuclei. And this is already the indicator that this wave function must be the one that is actually providing the bound state. So this is a state where the electron is mostly, or has a probability of being located between the two positive charges. And simply from the fact that we have a strong repulsion interaction between the two nuclei, it is obvious that this state is the one that compensates and leads to a bound state, whereas the antisymmetric configuration has a vanishing electron density between the two nuclei, and therefore no compensating effect with respect to the repulsion between the positive charges of hydrogen nucleus A and B. Therefore, this wave function, which we denote as antisymmetric or as psi minus, is a wave function that describes a state that is not bound, right? So if we look now, I think this is coming up here. If we look at the energy that we obtain as a function of the internuclear distance, right? So this is now the electronic energy as we calculate this, plus the interaction energy for the two nuclei, A and B. So it's just this standard Coulomb term that we first neglected, is 1 over 4 pi epsilon naught times 1 over RAB, with RAB being the distance between the two protons. And this all multiplied with the charges, which is simply 1E times 1E. That would be then our energy contribution, our repulsive contribution to the total energy, which then leads to a total energy for this molecule as a function of distance that looks like this, forming the bound state if we build our electronic wave function as a symmetric product. But it leads to a dependence on energy that looks like this if we build it with antisymmetry, where we have phi A minus phi B. Okay, so you can see in this case, the energy is always positive. So it's a state which is not bound. Or in other words, if I had a molecule in this configuration of phi A minus B as this total electron wave function, then at a given distance, here in angstrom, at a given distance of 1 angstrom, this system would immediately try to relax to its minimum energy state by breaking the bond, right? So it would dissociate and break into the two separate atoms in principle. So this is the hydrogen molecule, a simple single electron problem. It's a simple first introduction and a simple, comparably simple problem because we only have one electron, right? So we don't have to worry about electron-electron interaction here. So this will be the next step in our extension. So that's the introduction, H2+. What have we used? We used the linear combination of atomic orbitals and described the wave function as a sum or a difference of these two atomic orbitals. And we can, for each of them, calculate now the electronic energy as a function of the internuclear distance. And we get our potential energy surface in both of these possible electronic states.
May I ask something before we go on to the further steps? Could you go back to these overlap integrals, these types of integrals that arise? I was wondering, so I think one slide more back.
Oops.
This one, yeah. I was wondering why don't we do it? I mean, in this case, we did an integration and multiplied with this additional orbital BR, but why don't we use it with the complex conjugate instead of? It
is supposed to be the complex conjugate. It's just that,
okay.
yeah. So in general, the wave function has to be thought of a complex number, also a complex quantity. And so when I said multiply from the left, this is, I think I got this from Haken-Wolf. And you can see here, it was still denoted as phi A star and phi B star from the left. So it is the complex conjugate because it is in the Dirac notation, the bra vector that's coming in. And so they, in the text, I guess they said somewhere that we can assume a real wave function and then we just write it down like this. But in principle, there should be a star notation here since it is the bra vector coming from the left.
Okay.
Otherwise, our concept of saying that the absolute square of the wave function must be a real number and is representative of the probability wouldn't really fit here, right? It wouldn't work. So, yeah. Okay. Now, next step, a little bit more complicated. We look at the many electron problem with many meaning, at least now 2 for this first extension. We look at the neutral hydrogen molecule. So on the right-hand side, you can see the sketch with the distances and our nomenclature. We say we have atom A and atom B, and we have 2 electrons, 1 and 2. So we use 1 as the index denoting the electron, 2 as the index to denote the second electron, and A and B as an index to denote the nuclei. So we have distances, for example, RA2, meaning this is the distance between nucleus A and electron 2. How does our Hamiltonian look? Well, we have the kinetic energy parts for the 2 electrons, h bar squared over 2m naught. You can see here, this is all in SI, in SI. In principle, we will, on the computer, as I told you already, we are using the atomic units, which makes this all much easier to read and reduces the troubles when doing the programming. But that's how you would write it down in the SI units. So we have the 2 kinetic energy operator parts for electron 1 and 2. Then we have the Coulomb interaction of the electron 1 with the nucleus A. Then we have electron 2 interacting with nucleus 2. And then we have a mixed expression where electron 1 is interacting with the other nucleus and electron 2 is interacting with the first nucleus, right? So these are these cross terms. And then we have the repulsion terms. One would be the repulsion between the positive charges A and B, the 2 atoms or nuclei that remain. And we have the crucial term here, the interaction between the 2 electrons, 1 over R12 in our nomenclature, with R12 being the distance between the 2 electrons. So this is our Hamiltonian. And we would like to find now the corresponding energy. So we have to solve the Schrödinger equation H psi equals E psi. And the Heiter-London ansatz is an idea that approaches it from a point of view where we start with the solutions at very, very large distance. Because at very large distance, it's obvious that all the crossing terms and the electron-electron as well as the nucleus-nucleus interaction will vanish because they depend on 1 over r, which is basically in distance. So if this is far apart, we know that the solutions would be simply one single electron in the field of the nucleus. So it would be the hydrogen atom by itself without any interaction. We know the corresponding energies, which we have denoted here again as E naught. E naught, you can see here, is the corresponding eigenvalue for the atomic Hamiltonian of the first atom and the atomic Hamiltonian of the second atom. Since it's both hydrogen, we can write it as E naught in both cases. Now the idea is, since the actual Hamiltonian in the non-interacting system, right? So if we have it sufficiently far apart, then the Hamiltonian that is relevant is just H1 plus H2. Because all these coupling expressions are not contributing anymore because the distance between the particle is so large. And in this case, then the simple product function phi A times phi B would be a solution of this Hamiltonian at large distance. Okay, with this in mind, we just need to do one more thing. We need to anti-symmetrize the total wave function, because we know it's a fermionic wave function, which means that if I take an electron and I take another electron and I make them swap positions, the total electronic wave function must pick up a sign. In order to generate this, I can proceed as follows. And here you can see we have also done something else, because for up to now I was just referring to the electronic wave function of a single electron as phi a of R1, for example, meaning electron number 1 sitting in atomic orbital A, phi a. But the electron has also this intrinsic internal degree of freedom, the spin, and so to be fully accurate, I'd have to also address and write down the actual spin state. Okay, so that's what's happening here, and I'm doing the anti-symmetrization. I'm writing, for example, electron 1 sitting in orbital A, so it's R1 phi a, phi a of R1, multiplied by alpha 1. This is just our way of denoting spin up electron number 1. And the second electron is sitting in orbital B, so phi b of R2, and the second electron is also spin up, for example, in this wave function that I'm constructing here. And now, in order to arrive at a wave function that behaves as a fermionic wave function is supposed to, I will have to add another term, which is exactly the same term as we had before, just with positions electron 1 and electron 2 swapped and a minus. Because now we can see that if I change R1 into R2, the wave function is minus what it was before. It picks up the minus sign, and we have successfully anti-symmetrized the total wave function. This expression can be rewritten, so I have now pulled out the spin part, because it's in both cases first electron spin up, second spin up, and here it's also first spin up, second spin up, because all of them are spin up. So I'm taking the spin part out, and I can see that my total 2 electron wave function is antisymmetric, and it is antisymmetric because it is antisymmetric in the spatial part, whereas it is symmetric in the spin part. And if you multiply a symmetric with an antisymmetric function, you get an antisymmetric function, right? So we can say here that the total 2 electron wave function is an antisymmetric wave function because it is antisymmetric in its spatial part. In spin, it is not antisymmetric because both electrons are spin up electrons, and if I just exchange electron 1 and 2, nothing changes in the spin part. Okay, now there's another thing which we can borrow from our maths lectures of the past. Especially convenient is the tool of the determinant. From linear algebra, if you think about what it means to have a determinant of a matrix, look at how we write the wave function here. We say the wave function psi can also be written as a determinant of this expression. How do we create a determinant? We take the diagonal elements, a product of the 2 diagonal elements, minus the product of the anti-diagonal elements. So this is, in the case of the 2 electrons, a simple 2 by 2 matrix, which, if you take the determinant, creates automatically a antisymmetric wave function. So this is a convenient feature of the determinant, and it works for the obvious reason that the determinant does exactly what we would like to have for a fermionic wave function. Namely, if you think about linear algebra, what happens if you exchange, or let's start it this way. Look at how this determinant is written here. we can say it has 2 rows and 2 columns. In the first column, we have electron 1, and in the second column, we have electron 2. In the rows, we just have the first atomic orbital and then the second atomic orbital. Now, what happens to the determinant if you swap rows or if you swap columns?
You pick up a minus sign.
Exactly, you pick up a minus sign. So you see, by construction, the swapping of 2 columns is identical with changing the positions of 2 electrons. I'm taking electron 2 and put it in place of 1, and I take 1 and put it in 2. Is identical to switching columns in our determinant here. So you can see by taking the determinant, you have already created this mechanism that the particle exchange of 2 electrons creates a wave function of opposite sign. So this is the feature of the determinant. And then there is another feature, a constraint that follows from Fermi statistics and from this request that the total wave function has to be antisymmetric. What happens in case of having 2 electrons with exactly the same set of quantum numbers? The wave function must vanish, right? And so what does the determinant do if we have 2 columns which are identical? It again vanishes, right? So this is also fulfilled or shows how the determinant really catches all these aspects that we need. So in short, we can also write for more complicated n-electron systems, as we will do later. We can write the total n-electron wave function as a determinant, and it is a convention to write down the electrons in the column and the orbitals in rows, but either way would work. So it's up to you in principle. Okay, now we have our wave function. Okay, we say it's a determinant. How do we get the energy? Well, the energy is the expectation value of our Hamiltonian here. So if we take the wave function and we take its complex conjugate, we multiply from the left onto h and are hitting psi on the right, and we divide by the overlap or the norm of our wave function psi, we get the corresponding energy of this 2 electron system. So we'll have to calculate these 2 integrals, one of them the Hamiltonian sandwiched, and the other one would be the norm. Before we get going, a few words on the actual state that we have picked. The state that we have picked is a triplet state. Let me go back quickly. Why is it a triplet state? What does triplet mean?
Guess 3 states with the same energy generated.
Yes, exactly, right? So we have a threefold degeneracy as long as there is no magnetic field, because we have a total spin, which is 1. We have one half, but both electrons are spin up, so it gives us a total spin of s equals 1. So we have 2 times 1 plus 1, giving 3 possible orientations and energies in a magnetic field, right? So this is why it's called a triplet state. Okay, I can already tell you that this is not the ground state. You might have guessed already that the triplet solution is not the ground state of the hydrogen molecule. It's low in energy if we have the spins arranged differently. So let's see the other options that we have. We had the situation of both electrons with spin up, giving us s equal 1. We can also have both electrons spin down, right? So then our total wave function which has to be an antisymmetric wave function, will be again a symmetric function in spin, but now with both electrons in spin down positions, multiplied by our antisymmetric spatial part of the wave function. This would be the state that corresponds to our orientational quantum number ms equals -1. The one with both up would be ms equal 1. And we can also find a combination where the total spin s is 1, but the orientational quantum number is 0. And the combination that allows us to end up with this would be first electron spin up, second down, plus second up and first down, right? So this would be our combination. This is again symmetric in spin, but has a total orientational quantum number ms equals 0, belongs to this group of the triplet with s equals 1, and is one of them, namely the one with ms equals 0. And the ground state is a singlet state, which is written here on this slide 103 at the bottom. You can see here in the singlet state we have our antisymmetry generated by an antisymmetry in the spin and a symmetric spatial part. In total, by taking building the product, we again get an antisymmetric wave function psi. Here, note that the antisymmetry stems from this part here, because if you exchange 1 and 2, you'll see we again pick up a minus sign. One electron is up, the other one is down. First electron is up, second is down, and the other one is second is up and first is down. So if you change 1 and 2, it gets this minus sign. This is our singlet state and our ground state. Okay, now in order to calculate the energy, we have to evaluate this integral, or these two integrals. One would be this overlap, the other one would be the Hamiltonian sandwich, so the expectation value basically of the Hamiltonian for the given electronic state. And that's what we are doing now. Here we start with calculating the lower part, so the norm. And the only thing we have to do is now we come in with our expression for the total wave function, which is this anti-symmetrized product, which can be either plus or minus. So this is like the general solution that we are going through now for the case of being symmetric or anti-symmetric in the spatial part. It's coming from the left, so we have this complex conjugate, so that's why we have the star here, and we can multiply this out piece by piece and have in total 4 contributions. Oh, excuse me, we have two contributions, but each of them let's say it differently. We have 2 types of contributions. One would be contributions where the wave function that corresponds to the atomic orbital on the first and on the second are separated in terms of how we integrate, right? So we have integral over phi a squared times integral over phi b squared here, and for the next terms too. But then we have this other type as well, where we have an integration over this is now integration over the first electron coordinate, but it combines an electron sitting in orbital A and an electron sitting in orbital B, right? So you just multiply this out. You have an integral over these 2 electron coordinates, the first and the second, and then you see you have these types of integrals that pop up. And the second type has this sort of a mixed expression in it because we have an integral for over the first electron coordinate, but the electron is in A and in B, and the same is true for the integration over the second electron coordinate, where the second electron is also in A and in B, right? So these are the types of integrals that appear. But since the atomic wave functions are already normalized, this boils down to 1 times 1 plus 1 times 1. This gives us 2. And here, these integrals, they have a certain value. And this value is obviously dependent on the actual internuclear distance between the two atoms. It is the overlap integral. And we write it down as S. So S times S giving us S squared. And so in total, we obtain, therefore, for the normalization here of our 2-electron wave function, 2 times 1 plus minus S squared. And the plus minus, again, stemming from the fact that we're doing this at the same time for the symmetric as well as for the antisymmetric spatial 2-electron wave function. Okay, so this is the calculation of the norm. And now we get to the denominator of this equation when calculating the expectation value of the Hamiltonian, where we had our Hamiltonian sandwiched from the left and from the right with our antisymmetrized product of the two wave function of the two atomic orbitals. And this is broken into pieces here because so we have from left and from right basically these wave functions, 2-electron wave functions coming, which are these anti-symmetrized products. And so what's going to happen is that there will be 2 orbital products from the left meeting a product of 2 orbitals on the right. And this will be either a situation where we are speaking of electrons in a configuration where they are both in same or in different orbitals with respect to A and B. So this first situation that we're describing is from left and from right. Electron 1 is sitting in the same orbital A, and electron B is sitting in the same orbital B. Right? So this is one way of how these antisymmetrized products can meet. The other one would be that electron 1 in A and electron 2 in B meets on the other side electron 2 in A and electron 1 in B, right? So we have to break this into pieces and look at what are the values for all these parts of our Hamiltonian in these cases. So that's what's going on here. Immediately, if we write down the total Hamiltonian, we have again introduced the shortcut that the kinetic energy of the single electron plus the interaction energy of the electron with its corresponding nucleus is the actual atomic Hamiltonian. So we see immediately that H1 and H2 will be replaced or can be replaced by the corresponding atomic eigenenergy, right? Why? Because H1 and H2 are parts of the total Hamiltonian, which each of them only dependent on one electron coordinate, because it is the interaction of this one electron with this one core. And so if you multiply this out, H1 is only acting on the first electron, H2 only acting on the second electron, and so you can pull this non-relevant other parts of the atomic wave function over the operator and integrate. So you have this integral over phi A, phi B squared, and you have the expression 2 times E naught. This is the eigenenergies of H1 and H2. And then we have these remaining terms, which we are going to work our way through step by step. I have given the numbers 1, 2, 3, 4, 5. And here you can see what happens if we integrate this out. Well, the first one, since it's just a constant, just gives us this 2 times E naught. Then we have an integral of this type, we integrate over the first electron coordinate and have a phi a squared times this 1 over RB1. So first electron is sitting in orbital A, and we have now this interaction with the other nucleus at B. So this is a contribution we call C. It is identical due to symmetry for the situation of having electron 2, which stems from atom B, interacting with the nucleus of atom A. Right? This is also C, so this is just some constant. I'm writing C here because we would have to evaluate this, for example, numerically, if we know phi A from our solution of the atomic Hamiltonian, right? So this gives you some value C. Then the fourth term was a term which is basically just a constant because it doesn't depend on the electron coordinates. It is just a Coulomb interaction between the two nuclei. So this is just a number which depends on your molecular geometry, but it doesn't depend on the electron coordinates. And the last term is a term, and this is going to be the tricky term in the future when we deal with more complicated n-electron problems. This is the electron-electron interaction term. Again, this is from Haken-Wolf, I think, therefore it's in German. Wechselwirkungsenergie der Elektronen, EWW, has this phi A squared, phi B squared, and then the interaction is 1 over R12, with R12 denoting the distance between the two electrons 1 and 2. So this is the result of the integration for each of the terms in our Hamiltonian. So we can write this down as follows. So this would give us an E with this dash on top to distinguish it from the other E that we're going to calculate now. So it gives us 2 times E plus 2 times C plus this interaction energy and the constant 1 over RAB term, which stems from the Coulomb repulsion of the two nuclei. Okay, right, so this is 1/2 of the upper part of our ratio when calculating the expectation value of the Hamiltonian. Now comes this other part that stems from our demand to have a antisymmetric two-electron wave function. So we have to deal with this other part where we have electron 1 in A and electron 2 in B is now meeting electron 2 in A and electron 1 in B, right? So we are evaluating now these cross terms. This is indicated here. And is looking like this. So the operator is obviously the same, but what has changed is the structure of our product of the wave function here. You can see we cannot pair this anymore in terms of having squared expressions for our wave function, because you can see electron 1 does now this fancy thing of being in orbital A and in orbital B at the same time, right? So it is an expression for the probability of electron 1, which can't really, which doesn't correspond to our concept of a density anymore, right? Because if it's phi A squared, it's the electron density, and I have a clear picture of what it means. But due to this request that we have an antisymmetric wave function, we also have these mixing terms, these exchange or Austausch terms, which lead to a function that has now a mix of both atomic orbitals, right? So for the first electron, A and B mixes, but also for the second electron with coordinate R2, A and B are mixing. Okay, so we have again to evaluate all these integrals. Now this is almost the same as before.
Can I ask about that?
Sure.
Short question. If you could go back,
Mm-hmm.
I think I'm mixing something up, but right now I'm having difficulties to see why the first term is just 2 times A naught, because you are multiplying the Hamiltonian to to an atomic orbital that is located somewhere else, namely at the position of the other nucleus, why does it still evaluate to give E naught? Do you understand my question?
Mm-hmm. Okay, so the first part would be the single electron Hamiltonian, right?
Yes.
So yes, for the for the electron in the field of just one nucleus, and if you have now H1, for example, and you have this product here, then you can see that the only phi A and phi B are the ones that interact with, or are the ones that depend on the first electron coordinate. And you would be right, it would be different if the two atoms were different. But since phi A is identical with phi B, since it's the same atom, it gives you again E naught.
Okay. So R1 and R2, they are not in this sense absolute coordinates, but they are coordinates relative to the nucleus.
They are just, yeah, they are just, this 1 and 2 is indicating what type of electron this is, the first or the second. And so this is what it means. And if I say now I take the first Hamiltonian, so this is the one that has the derivatives with respect to the first electron in it and describes the Coulomb interaction with the first nucleus.
Yeah, and I think that the Coulomb interaction is the one I'm having trouble with, because the kinetic one, I see that it is the same.
Yeah. But if you take the Coulomb potential of the first atom and you take the electron that actually belongs there, it gives you the energy. But now you take this away and you take the other electron and put it there, it gives you the same energy, right? So you have to see it like this. It has a different index because it's the second electron, but it is sitting in this orbital that is at the first atom. So in this case, it again gives you then the E naught energy.
Okay. Because I was thinking you're not exchanging the index, but you're exchanging the function. I was thinking you're not taking the same orbital but putting another electron there, but rather you're taking the same electron, but rather you're changing the function, going from phi A to phi B and taking the same electron. But maybe I should think it through myself.
Mm-hmm. Okay, yeah. I'll think about it myself. Or maybe I can explain this in a better way, but yeah, so I would see it this way. So phi A and phi B are only different in the sense that they belong to different nuclei, but they are the same type of wave function because it is the same element, right? So phi B and phi A look exactly the same.
Yeah, only that in the denominator of the corresponding fraction, there's another position of the nucleus, isn't it?
But the wave function does not have any other coordinate in it. Phi A and phi B is only a function of the electron coordinate. And the actual position comes in from the expression in the operator.
Okay. Yeah, maybe I have to think it through.
Yeah.
I have some idea now, but it doesn't completely make sense, but I think maybe it's too much of a waste of time.
I see where you're coming from, because technically A and B are wave functions that are located at different atoms. Yeah. But in principle, if you just look at if you write this as an electron density, electron distribution for the first and for the second electron, then if you take the square, the electron distribution is the same for both scenarios, for both atoms. And what's denoting or what's coming in here in E naught is the kinetic energy operator and the 1 over R 1A and 2B terms, which is the only ingredient basically that introduces then the absolute position somewhere in space, because this is what tells you if it's either A and B, but since it's the same atom, it gives you the same energy E naught. But maybe I have this on the now. Okay. The thing that remains though is, because it's the if you take the first Hamiltonian, for example, the first atomic Hamiltonian, which depends only on the first electron coordinate, then you have to integrate this out, but the second electron coordinate is not affected, right? And it still meets because you come in from the left with orbital A, for example, for the second electron, and from the right with orbital B for the second electron. So if you multiply it out, the difference that in comparison to before is that if you multiply this out, this doesn't give you the normalized wave function, but gives you also the overlap integral as another factor that appears. So this gives you s squared for the first term. And if you look now at the other terms that appear, so we have the 1 over RB1, so this is this cross term of electron 1, which belongs or belonged originally to atom A, interacting with the nucleus at position B. So this is an operator that obviously depends on the coordinate of the first electron. Therefore, the integration over the first electron coordinate has to be done and leaves us with some numerical value, which we denote as D. And the operator is not a function of the second electron. So the wave functions with respect to the second electron are meeting each other directly and give again rise to a overlap contribution S. So this gives us SD. The same thing, just thought the other way around, is the interaction of electron 2 with nucleus A. But due to the symmetry of the problem, us having the same atoms, A and B, it again gives us an S times D. Then the term core or nuclear interaction, this repulsion contribution, again, is not a function of any electron coordinate. Therefore, it is overlap integral times this value that you get for a given internuclear distance. And finally, another term, and this is the second complicated and challenging term, again, the electron-electron interaction, but now without this classical representation or classical analogy we had before, because now we have the 1 over R12 term. It is a clear 2-electron operator because it's dependent on the positions of both electrons. So we have to integrate over this for either first and electron coordinate. But you can also see that we have this weird situation of having electron 1, denoted by R1, sitting in orbital phi A and B at the same time. And the second electron again sitting in orbital A and B at the same time. So we do not have this classical picture of two smeared out electron density distributions in space just interacting through Coulomb interaction, right? So this is the so-called exchange energy contribution or Austauschwechselwirkung. So this is the Austausch, and here if I go back to the situation where we had it nicely, where we had the same electron in the same orbital on both sides. In this case, you can see what happened was we had phi A squared times phi B squared. And so each of these terms is basically an electron density distribution. So it is two smeared out electron densities in space. And I can, with classic electrodynamics calculate the energy of this situation. So this has this analogy, but our demand of having an antisymmetric electron wave function also introduces this weird term, which we call the exchange interaction, which has no analogy because it's no longer a well-defined electron density that interacts with some other density, but a product of two wave functions, A and B. And now, to do it as we did before, we collect everything and write down this energy expression that stems now from these crossover terms as E tilde. It gives us the four terms as we just had them on the previous slide. And knowing both, I can now write my energy, the total energy, for a symmetric or antisymmetric wave function as 2 times and then this E dash plus minus E tilde over and then the the normalization that we calculated before. So I obtained two energies because we did this at the same time for both types of wave function. Here denoted as G and U for gerade and ungerade. And you can see the contributions. We have 2 times E naught, which is the atomic energy contribution. Then we have terms, one stemming from the meeting of the electrons in the same orbitals, and then a third term, which is stems from the meeting of 2 electrons in different orbitals, right? So this gives us this exchange energy contribution. This is the third term, and then just another term that stems from the nuclear repulsion between the 2 positively charged protons. And if you calculate these integrals based on your solutions of the Schrödinger equation for the hydrogen atom, you again get a picture that looks basically like this. Energy as a function of distance when calculated for different distances, R, A, B, gives you in the gerade state where you have an anti-symmetry in spin because we are symmetric in the spatial part. This gives you the bound state with a clearly defined minimum, which we call then the equilibrium position, because this is where you will find the molecule most with the largest probability. And we have a state which is antisymmetric in the spatial part and symmetric in spin. So this would be the high spin state, which is for this molecule consisting only of 2 protons and 2 electrons, an unbound state, showing the similar behavior as before, the minimum energy lying at infinite distance. So this molecule in a spin-up position would love to break apart and form 2 separate neutral hydrogen molecules. Okay, so this method we call the Heitler-London approach is a nice first step, and it gives us a bound state and a good approximation of the actual equilibrium distance, but the theoretical binding energy is still quite far from the experimental value. So it is just an approximation, and we would like to improve on that. Now let me introduce you to a slightly different approach to the very same problem. Okay, so we are again looking at H2, but now we choose the ansatz of Hund, Malikan, and Bloch, which is the approach that we're going to extend on in the next lesson because it is the fundament of our Hartree-Fock approach later on. It is, in this case here, it is in principle, or it is less accurate, but allows this systematic improvement. because it's based on the concept of molecular orbitals, which we will fill up with electrons. So in this Heitler-London approach, we said, okay, we look at the systems at separate distance. We have a hydrogen atom here, we have a hydrogen atom here. What are the solutions for this system? And if I know them, how can I use this information to make a good approximation for the actual total system? That was Heitler-London. And in Hund, Malik and Bloch, we say, okay, here we have atom A, and here we have atom B. And these atoms provide us with atomic orbitals, and we will build now our n-electron wave function from a set of molecular orbitals. These molecular orbitals will be anti-symmetrized as we did before, but they are also built as linear combinations from the orbitals we have on both sides. Okay, so this is the idea, introduces this concept of molecular orbitals. We say molecular orbitals are a linear combination of our atomic orbitals, and we build the total wave function again as an antisymmetric or antisymmetrized product of these orbitals. In the case of the hydrogen molecule, the two approaches, Heitler-London and Hund, Malik and Bloch, are very, very similar to each other, because the separate system having an atom on the left and on the right-hand side, each of them, if you look at the solutions, are the atomic orbitals, right? So in this case, the two methods are like very closely related to each other, and I'll show you on one of the next slides that they can be translated basically into each other. But the ansatz or the concept in the Hund, Malik and Bloch is a little different, because I say, okay, I'm borrowing the concept of atomic orbitals, and I'm also using it for my molecular system. I say there is also something like a orbital, which is something like a single electron wave function, and I can build it somehow from the orbitals that I have at hand and put electrons into these molecular orbitals in the same way as I would be putting electrons into atomic orbitals when filling up the atomic system with electrons, right? So it's just using this idea as we see it as the real analytical solutions for the atomic system, for the electron in the field of the nucleus, where we have all these eigenfunctions with 1s, 2s, 2p, and so on. We use this concept and also apply it to our molecular system. Okay, enough about the intro, so let's get going. What's happening? We write the total wave function, in this case, psi of R1 and R2. This is a little weird. Let me see why it's written. No, it's not saying this anywhere. Okay, so please don't get confused. I see it now for the first time that R1 and R2 are uppercase. This is weird. They should be lowercase. This has nothing to, it's a little bit confusing. Yeah, so these are electron coordinates, first and second electron, and we do the following. We build a molecular orbital, which is denoted as psi g for gerade, which is a linear combination, and in the case of this traditional or of this historically Hund, Malik and Bloch ansatz for hydrogen, same prefactors for both and just normalized, right? So this is our psi g. I say it's a linear combination of A and B orbital, and this linear combination I call my molecular orbital. And then I say, okay, I put the first electron and I put the second electron in this very same orbital psi g. So this is obviously now symmetric with respect to its spatial part of the total wave function. So it has to be anti-symmetric with respect to the spin part. Or in other words, also for molecular orbitals, we stick to the Pauli rule that we cannot put two electrons with the same spin into the same spatial orbital. They have to be different in spin. Therefore, the spin part of the two electron wave function fulfills the need of anti-symmetry. It picks up a minus sign if we exchange electron 1 with electron 2. Okay, so this is the answers, and with this I would do the same thing. I would come in with psi star from the left and with psi from the right, calculate the expectation value of the Hamiltonian and get an energy. In this case, you'll see it is slightly higher than the prediction of Heitler-London, which might be first a little confusing because it gives it has actually more terms in the treatment, but it is also or it can be explained by the fact that it is an actual mixing that does not improve the description of the actual ground state. And you will see this on the next slide. In principle, what we are going to do is we will stick with the Hund, Malik and Bloch approach, and we will form our molecular orbitals as a linear combination of atomic orbitals. The thing why it's not much better here for the hydrogen atom is that a very specific linear combination is chosen here in this historical ansatz, namely A and B fully the same with same coefficients, and taking this sum to form the ground state or the lowest molecular orbital just through this linear combination and work with it this way. Let's compare them now. So Heitler-London, the first one I told you, was the one where we said, okay, we take a product, and the product is simply the solutions at infinite distance. At infinite distance, it breaks into this system of having H1 here and H1 there. So we have phi A and phi B. We just have to anti-symmetrize the total 2-electron wave function. That's what we did in the spin part, and for the spatial part, we had it in this symmetric shape. Remember, that's how we were speaking about the ground state wave function in this spin singlet state looked like this. What I can do now with Heitler-London is I can also think about the alternative of combining the orbitals I have at hand. So right now I'm just saying, okay, we have electron here and an electron here. We have this solution, we combine them and then we're done. But what about the situation where actually both electrons are sitting in the same spatial orbit? So having both electrons, for example, sitting at atom A, or both electrons sitting at atom B. That's also something that I could consider as a valid contribution or a possibility of the system. And this is what I call Heitler-London plus ionic character. I call it ionic because this would mean it is an electronic configuration where both electrons are more likely to be found on one position than on the other. Then this would be negatively charged and the other proton would be basically naked, no electron around it, so it would be a positive charge there, and then it would have a strong ionic character, right? So I can say, well, in principle, I can also write my psi gerade, my 2-electron wave function for this system, as a linear combination of both of these, of the neutral and the ionic description. And this Heitler-London plus ionic and Hund, Malik and Bloch, I mean, if you multiply this out, you can see that this is going into each other. It's basically giving you the same result depending on what you choose for the coefficient C in this linear combination of neutral and ionic character. And this slide 113 should illustrate this a little bit and show that these two approaches meeting each other for the hydrogen dimer, for the hydrogen molecule. Look at this idea. We take the wave function at atom A and we take the wave function at atom B and we say, okay, let's try to improve it by adding a little bit of B to my atomic orbital of A and introduce this as a new type of orbital. So we allow a kind of a mixing, a gradual mixing, and this gradual mixing is written as d times phi. So please don't get confused. This is not a derivative expression here. This is just some constant d multiplied by phi b, and this d is something I'm going to change from 0 to 1. We say our gerade wave function for electron 1 and 2 looks like this. We say it is as we had before. So look at Heiter-London as it's written here. First electron A, second B, or second A, first B. And now instead of using A and B, I'm using these mixed expressions, A and a little bit of B, and here B and a little bit of A. So this is shown here, A with a little bit of B, B with a little bit of A, and same for the second part for these two. This would be then A, second electron in A with a little bit of B, second electron in A with a little bit of B, and first electron in B with a little bit of A. And if you multiply this out, you get this expression as it's shown here on this slide. And you see if you set D to 0, then it would be the Heiter-London ansatz. So then it is just what we had before. It would be exactly this expression, pure Heiter-London without ionic character. And if I set D to 1, it would lead to this Hund-Malick-Bloch ansatz, which was this expression here. So if D is equal to 1, then we make a full mixing and we say the orbitals are a mix of A and B. Okay, so you can see that you can switch basically between these two extremes of having no mixing at all and the full mixing, 50-50 mixing of A and B, to lead to either Heiter-London ansatz or a Hund-Malick-Bloch. And the idea now is that for this simple system, everything is sort of fixed by the fact that if you look at the normalization constraint of the total wave function, all the coefficients are fixed and there is no, simply through symmetry and what we discussed, everything can be calculated and we get the energies as I have shown you before in the case of Heiter-London and as I indicated for Hund-Malick-Bloch. If you have now a more complicated system with many electrons, then the question raises, how are you combining the molecular orbitals? And you will have to find a strategy that finds the best combination of your atomic orbitals to build molecular orbitals which are the lowest in energy so that you can occupy them with all the electrons that are in the system. And so we will need a numerical method that finds us this lowest set of atomic orbitals, of molecular orbitals, to be occupied with our electrons that we have in the system. And so this method will be called the Hartree-Fock approach, and we will dedicate the whole session to the Hartree-Fock approach next time. But it is based on this Hund-Malick-Bloch picture. So we are going to work with the concept of molecular orbitals. We say molecular orbitals are built from atomic orbitals. And the whole idea of Hartree-Fock will be to find the best linear combination of atomic orbitals that gives us the set of a set of molecular orbitals which are lowest in energy. They are going to be filled with electrons, and this will be our expression for the n-electron wave function. So that's how we're going to solve this problem. Okay, so this was more like a historical overview. We have these two approaches. We see that they are basically meeting, and for the specific system of H2, they are almost identical to each other, just conceptually a bit different, but can be translated into each other. And the idea of the molecular orbital is useful and can be easily extended to more complicated problems where we cannot use simple symmetry constraints as they are given in this simple system of just having 2 electrons and 2 H nuclei. We will have to find a numerical way to define the correct coefficients in our linear combinations for these orbitals. And just as to give you a glimpse of this linear combination of atomic orbitals, And to link this to something that you know already, I will dedicate the last 2 minutes of this today's session to the concept of hybridization, because you've heard this before. You have probably even worked to some extent with it, or heard it in chemistry courses. So in principle, when you think about what is a suitable combination of atomic orbitals to form a molecular orbital, symmetry is always a good thing to start with. And all the chemistry of life is built around the carbon atom, which is very specific and stands out in the periodic table in the sense of size of the atom and its actual electron arrangement in the valence region, right? So because we have, in the case of the of the carbon atom, we have these 4 electrons in the valence shell, which is the 2s and the 3p. So we have 1s doubly occupied, then we have 2s doubly occupied, and then we have 2 electrons in the p block. With the p block, here we have the 3p, the 3 different types of p orbitals. If you pick a Cartesian basis set x, y, z, you remember the lobes. And so we have 4 valence electrons, and we have, in principle, the 2s as our valence shell and the 2p x, y, z, giving us 4 atomic orbitals to work with. And now it depends on what kind of interaction we form with other atoms, what kind of combination of s and p is more or less useful to form a certain type of bond. Let's have a look at this molecule here, ethene. We have a linear molecule, and we have a triple bond between the 2 carbon atoms. So how is this formed? And in order to derive now the shape of these molecular orbitals that are here in place, you can start with the atomic orbitals from each of the partners, in this case carbon and hydrogen, but you will use a certain symmetry thought to get already a properly pre-combined symmetry adapted state of atomic orbitals to form molecular orbitals with the atomic orbital of the other atom. So in the case of the ethene, we have this sp hybridization, where you just say, okay, I'm taking the 2s and I make a linear combination with px. I'm making psi s plus psi px, and I'm making 1 psi s minus psi px. This is an s orbital and the p orbital put together, one with opposite sign. And this means it leads to this kind of lobe that is either pronounced to the right or pronounced to the left. Okay, and now you see what this molecule is doing. At the C atom, we form the sp hybrid. So one cone goes to the right, one cone goes to the left, and it forms an overlap with the 1s orbital of the hydrogen. And this is our CH bond that we see here indicated as this line here. It's the sp hybrid of carbon longing over to the H and overlapping with the S of the 1s of hydrogen to form a molecular bond. Okay, so here a symmetry adaptation has taken place. We have linearly combined the S and the P at the same atom to form these 2 different lobes, one going to the left, one going to the right, to have H on both sides bound. And then we have still on each of the carbon atoms the two other P orbitals. P, let's call them now, because I said Px, then say it's Py and Pz, for example, right? So I'm taking then the 2 Py orbitals, and they form in this configuration another bond between the hydrogens, and I have the pz that, for example, are in this direction, and they form the other bond. So this forms the triple bond between carbon. Okay, so you can see there's a certain choice that the nature or the system chooses simply due to symmetry constraints. We only have two hydrogen atoms here. We have the carbon. Carbon would like to form to have this octet rule fulfilled, meaning that we have this kind of noble gas state with 8 electrons in the valence shell, basically. And here it would be arranged to this symmetry adaptation of S with P, with one p-type and orbital, and the other two p orbitals are left as they are. Now, in the case of sp2, for example, in the case of ethene, the situation is a little bit different. And here it makes sense to make a pre-combination of atomic orbitals that allows us to form a 120-degree shape. So we have this kind of shape for our orbitals. So we take, for example, px, py, and the 2s orbital, and form these three lobes that are with 120 degrees separate from each other, right, in the direction. And this is something we do at the C atom here and at the C atom here. And now each of these lobes overlaps with the s orbital of the hydrogen, forming the bond here, 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 and here. Then we have one lobe reaching out to the other lobe of the other C atom, which forms one bond. And what is still missing, or what is still remaining? So in sp2 we have used one s orbital and two p orbitals. So what's left?
The pz.
Exactly, the third p orbital, let's call this pz, for example. It would be the orbital which is now in projection here on this map. It would be the one that's pointing out of the screen. And this forms another bond and is the second bond which is found between the two carbon atoms, right? So you see, in this case, the atoms arrange in a way where a different pre-combination of S and P is the energetically most feasible structure. So it depends on what is offered to the carbon atom, how many hydrogen atoms, for example, are there to form the bond with. And as you might remember from chemistry, this is more stable than this configuration. And this configuration is less stable than the methane configuration. So if you have the carbon atom fully saturated in this way with 4 hydrogen atoms, this is a more stable configuration than the ethene configuration, for example, with a double bond. You might remember double bonds are kind of easy to attack and tend to react, and even more so the triple bond. So in this case, the sp3, here I would take one s and the 3p and linearly combine them to get the tetrahedral angles, right? And so you can just see that simply from symmetry, you can also derive already how linear combinations might look like in a molecular system. And on the computer with the Hartree-Fock method, we will implement a method that in an iterative way finds us these orbitals automatically. But molecular orbital theory and just concepts of symmetry are highly useful to understand. And simply by looking at what I've shown you here, you can derive certain features that are then macroscopically relevant, such as reactivity or melting point or whatnot, simply from this molecular orbital theory. So it's a very powerful concept, and we will use it a lot in molecular physics as well as chemistry. Okay, so that's it for today. If you have questions, please shoot. In the meantime, I will also start the feedback round. Today's code is QALBT. And we have 3 questions. I start with the first. What is an atomic orbital? Options: the solution of the Schrödinger equation for an electron in the Coulomb field of a nucleus. B, an estimate for a total electronic wave function of an n-electron system. C, an eigenfunction of the atomic Hamiltonian. Or D, the probability of finding an electron somewhere in space. Second, how does the 1s orbital of single oxygen contribute to the bonding in O2? How does the 1s orbital of a single oxygen atom contribute to the bonding? What's your guess? Bonding, anti-bonding, it doesn't care, or there is no 1s electron in the system? And the last question, from 2 atomic orbitals we can form 2 molecular orbitals. In the case of H2, one is bonding and the other one is anti-bonding. Why is the splitting of relative energies not symmetric? So if you form the orbitals and you look at the energies of these orbitals, bonding and anti-bonding, then you will see that the anti-bonding is higher in energy with respect to this energy you had before for the separate system with the atomic orbitals. Then the lowering is lower after having formed the bond. Why is that? Options: because nature prefers bonding. B, due to the overlap. And C, it would become symmetric at infinite internuclear distance. And the last is because of spin. And I see that, yeah, we have already, even on the last question, 21 people already with answers. That's great. I think I'll probably stop. And we can go through the answers together. Okay, I see. So that's not bad. Most 88% found one of the answers that is correct. It is the solution of the Schrödinger equation for an electron in the Coulomb field of a nucleus. So almost everybody had this one, but only the approximately half of you also chose the second correct answer, an eigenfunction of the Hamiltonian for the electron in the atomic hydrogen. It's the same thing, just said a little bit differently. Second question, how does the 1s orbital of a single oxygen atom contribute to the bonding? And the correct answer is it doesn't care. 63% had the correct answer. Some decided to go for bonding. If you think about the energy difference between the 1s and the 2s, you can see that typically any type of chemical interaction never touches the innermost orbital. So they are basically not affected at all through chemistry that's going on. And therefore, even after doing the linear combination and whatnot, even if you do a Hartree-Fock calculation and you get all this minimum, or you get all the molecular orbitals, you will see that the lowest molecular orbitals in O2 are the 2 1s orbitals of the oxygen atom. Okay, so in this case, it's a linear combination that's not very exciting because it is simply the atomic orbital we started from. There's no better approximation than what's already coming from the atomic solution because there is no real interaction between electrons that changes the electron density near the core. And the last question is from two atomic orbitals, we can form two molecular orbitals. In the case of H2, one is bonding and the other one is an antibonding orbital. Why is the splitting not symmetric? And here you got, so 50% got the due to the overlap, which is the correct answer. It is this overlap, the S. But if you think about the, because if you think about how the energy expression looks like, it was this 1 plus minus S, right? And this plus minus is the thing. Because in one hand you increase, in the other one you decrease the number under, and therefore it is a little bit asymmetric. But it would become, in principle, symmetric at infinite distance. So if you pull them apart, why? Because the overlap integral is starting to vanish, and then it is in the end this symmetric combination of both. But it's also a kind of a fancy way of formulating the question, I guess, because at infinite internuclear distance, the actual orbitals are the atomic orbitals themselves are the optimum linear combinations to form the molecular orbital, right? So they are then identical to the atomic energies, obviously. All right, okay, so thanks for participating.